Okay, hello and welcome to your first, I think this is actually my only video in regards to statistics. So we are going to start strong with chi-square. So this is a test of association. It is in 4.1, so we are going to practice it, but it's not really the best form of stats to use on like an IA or something. But you still have to... Obviously, you still have to know all about it. So let's get into chi-square. So basically, it's just a statistical tool to determine whether there's an association between two sets of categorical data. So this is just seeing if there's like a probability of an association by comparing observed values, so what you actually see in like a quadra, or like out in the field, so like observed values versus expected values if there was no association. And we're going to get into like how you would actually figure out those numbers, but the key here is that it needs to be categorical and not continuous, right? So categorical would be like the species found in a 1 squared meter area in a lake or something, or like, I don't know, in a marshland. Location, presence of a certain gene, like a yes-no category. Whereas continuous is something like height or distance or data or time, just like something that has an infinite number of values. We really want to stick with like the yes-no category, okay? So when we're doing chi-squared, we're looking to see if the presence of one species is associated with the presence of another species. That's as far as I want to go with chi-squared. You can use this for more advanced things, but I don't want to get into that right now. So we're just going to look and see if the presence of one species is associated with another. And you have two versions of a hypothesis with this. A null hypothesis is always going to be there is no association between the two species, okay? So there's no connection, no relationship, there's no association. Whereas an alternative hypothesis is that there is an association. And within that, it could be positive or negative. So either the species associate with each other, okay, that's positive, right? They like each other, they interact. Or they don't associate, and that's negative, right? They hate each other, they're mad at each other, whatever it may be, they don't talk to each other. So for our problem question, we're going to see if species A and species B interact with each other, okay? Species A is going to be acorn barnacles, species B, the sea stars. So our null hypothesis here is that there's no association between the acorn barnacles and the sea stars. For our alternative hypothesis, we have the positive and the negative. Either they're found together or they're not found together. Okay? This is like a crazy slide, but this is how you would gather data. You would look at all of these different quadrats and determine, are sea stars present? Are barnacles present? Yes or no, right? We love yes or no questions. And then you can see that, and maybe it's a little hard to see on your screen, but you can see that there's 4 different colors here. So if it's yes and yes, it's blue. If it's no for sea stars and yes for barnacles, red. The opposite is green, and if it's no for both, then it's yellow. And the reason that I color-coded this is because now you have these numbers, right? I'm not going to make you count them yourself. That's crazy. But there was 100 quadrants combined total, and you can see our actual data put into these 4 numbers. So just a breakdown of the data to make it a little bit easier to manipulate. Typically, in an IB test, you will be given the data like this slide, where it's already counted up and given to you, not like the table on the previous slide. But I'm just trying to be thorough here so you understand where these numbers are coming from. And now we're going to set up a bunch of tables like this so that you can figure out, or you can see how we're getting the numbers we're getting. So first, this is our observed data. So this is based on the numbers that we got from the literal data 2 slides ago from that huge data table. Okay, so we're just filling in this table, okay? Like in this top left box, all of the quadrants that had both species A and species B present is going to go into that square. And you can see that as I fill them in, it's the exact same numbers from the previous table. And then we're going to total them up on the sides. And what do you know? I get 100. That makes sense because there was 100 total quadrants. And I should have, I should have a data piece from each one that I already measured, right? That makes sense. That's why I have a total of 100. If your numbers do not match up to the total that you know you should have, you counted wrong. You need to go back and you need to do it again. But in this case, it all worked. So this is our observed data. This is strictly based on the actual quadrants that we looked at and the data that we got from it. Observed. Now we can calculate the expected data. So in this case, we're going to calculate what we would expect if the null hypothesis were true, meaning that if there was no association, okay? So here's your formula that you're going to use. So the column total times the row total divided by the total number of quadrants. Okay, so let's do this math and calculate the expected values. Now you can see them up here, right? To get this blue box, we took the column total, the row total, and then divided by 100 because we know that there's 100 total quadrats, and we got 37.3. And I just did the same exact thing for all of the other numbers, and I ended up with these percentages, or decimals. When we're doing this sort of work with chi-squared, you should always round to the tenths place. Okay, so expected frequencies is if there's no association, you just use this formula, figure out your decimals here, and then you add them up again to get your totals, and if you did it right, you should get the same exact numbers. Okay? So this is how you know you did things right. If you did it correct, you'll get the same totals. Beautiful way to check your work, right? And now the actual, I don't know, piece de resistance here. We're going to actually calculate the chi-squared value. This is like the only thing you did all of that work just to get to this point, and this is like the actual value to determine the statistical analysis. So, you know, lots of steps to get to this easy part. So there is this like really intense formula, right? So this right here, chi-squared, equals the sum of your observed minus your expected squared divided by your expected. And you just do that math and you will get different numbers, but we'll go through that together. So in this case, we're going to calculate the chi-squared value for each combination here. So remember, we had our observed numbers from like 2 tables ago. We just did our expected numbers. We square that number and then divide by our expected number. In this case, we got a really small number, right? 0.01. That's tiny. They're not always going to be that tiny, but in this case, maybe you're sensing what's coming, okay? But tiny numbers, in this case, you will round to the hundredths place. You do all the math for the observed and expected numbers. You end up with a beautifully filled table, and then you have to sum it all up. So you add all of these numbers together, right? That's the point of that like weird E looking thing. So you add them all up, you get 0.09. That is your calculated chi-squared value, 0.09. That's why it has that like explosion behind it. That's the most important piece of this formula that we're doing. This is the calculated chi-squared value. And then you just determine if you accept or reject your null hypothesis. And you do that by determining if it's statistically significant or not. Based on our contingency table, like the tables we've been using throughout all of this, it always has 1 degree of freedom. Okay? You do n minus 1. So number of rows, minus 1, number of columns, minus 1, n minus 1. And so we had 2 rows, 2 minus 1 is 1, times 2 columns, but minus 1, so 2 minus 1 again is 1. So you do 1 times 1 is 1. So this type of table is always going to have 1 degree of freedom. Okay? So you will be given this table. You will never, ever, ever have to memorize that. Now, that would be wild. That would be crazy. So 1 degree of freedom, this is the row we care about, this top row. And 0.05 is always the determinant of if it's statistically significant, okay? This is the kind of critical value. So our critical value here is 3.84. Oops, sorry. 3.84 because that is our degree of freedom and the number under 0.05. So critical value 3.84. Now, this is like the conclusion of our statistical analysis. The value that we got when we did the chi-squared analysis was 0.09. If it's lower than 0.05, we accept the null hypothesis, then whatever our critical value is, right? So if 0.09 is lower than 3.84, right, our critical value, then we accept the null hypothesis. If it's higher than our critical value, which was 3.84, right, then we reject the null hypothesis and we conclude that there is a significant association. Well, just to make sure we're all on the same page, right, if it's significant, it means that it's not due to random chance, okay? If you find something that's significant, it just means that it's probably real, okay? If you can reliably get significant data, it means that whatever you're doing has an actual effect on the data you're collecting. Otherwise, you might have just gotten lucky, or there's no real relationship and you're just measuring sort of like a normal occurrence. So our conclusion, this is like what you would write for your conclusion, okay? You have your calculated chi-squared value of 0.09. That is lower than the critical value of 3.84, right? So 0.09 is what we calculated when we added up all of those like blue, red, green, and yellow squares. And 3.84 is what we got from the table. That's just a number that is given to you. You have to you have to just look at the table to get that. You don't do any calculations for that. So 0.09 is lower than 3.84, which means that you accept the null hypothesis and you can conclude that there is no significant association between the sea stars and the acorn barnacles. Okay, it's random. Okay, we are going to do some actual practice with this, so if this was confusing, this is why we have notes, and we'll be doing this in class, and we'll be doing 2 additional practice problems just to make sure that you guys are getting this sort of stuff. All right? Great job.